we're at a time with an enormous amount of change happening in AI. And I think it can feel like every day there's some new news story, and it's pretty hard to predict what to do with it. But at the same time, we also are at a time when AI, people are making enormous bets in AI, putting billions and billions of dollars behind particular ideas. And those might feel a tension, right? You might say, well, why are people willing to put billions of dollars behind an idea that it seems very unpredictable? And what I'm going to argue today is that it's not unpredictable at all. Actually, there's some very deep regularities that mean that you can actually predict what is going to happen with AI. And if you understand those, you can make much better decisions for your businesses, for your governments, and for the world. Okay, so that seems a little abstract. I want to start by bringing us to a very concrete place, and that is supermarket demand forecasting. Okay? Something we should all be very clear and happy with, right? So this is something where every grocery store has to say, like, how much should we order, have the right amount on the shelves so that when our customers come in, we actually have the right things on the shelf. And of course, it really matters because if you order not enough, the shelf is empty, your customer is unhappy. If you order too much, then if you order some things like, bananas or something, stuff just goes bad, so you lose a lot of money. So they really care about getting this right. And it turns out that historically the way that people did this was with these sort of traditional models based on historical sales. So you'd say, well, okay, how many bananas did I order last year? And this year, we've got a little bit more demand in our area. We've got some things. We should order a few more bananas. And so typically, the general manager would look at the order and they'd say, oh, let's bump that up a little bit. Okay, so that's how this was historically done. And in this particular case study, so this was a case study that my lab did, we actually looked at a particular store. And we said, okay, they said, we're going to use AI to do better at making our predictions. Fantastic. And here's what happened. First of all, there was a big win in terms of success. The amount of error that they had in predicting how much would be bought went down by 1/3. That's a big deal in this area. And also, the costs of developing it and running it all of the time were so high, they initially paused development, and then they went forward later with a sort of much more measured version of development. Okay. So hopefully this is raising a couple of questions in your minds, right? This is saying, well, why are they spending this much, right? Why is it costing this much? And if it's worth so much to them, what's going on? Okay, so to help think about what's going on in this situation, and more generally why AI is being so successful, I want us to think about another question, which is, imagine we were doing this, right? And we were trying to predict the amount of ice cream that would be purchased next week. Okay? This feels like a pretty easy thing, right? We just said the natural way to do this is to look at maybe how much ice cream was bought last week, maybe how much was bought last year. But actually, if you think about it a little bit more, you might say, well, actually, we can probably do better than that, right? So we could say, well, we could look at competing products. How much of those competing products are bought, right? Maybe it's the case that some new brand has come out with some new flavor, and everyone's going to that flavor. Okay? Maybe it's the case the temperature matters a lot. So one of the things that really came up when we were doing this case study is people were like, oh, you have no idea how important it is. If you have a little bit sunnier day, suddenly the purchase of ice cream will go way up, right? People get very excited about that. Okay. How about events? So it turns out that, particularly in the United States, guacamole is hugely driven by whether there's a sports game on that game, right? So I imagine that there must be a corresponding thing here where there's a big football game, right? There must be some purchases that are done. Okay, you can imagine like the health trends that are going on. You can imagine more broadly trends that are happening. And you can also think of like interdependencies between these things, right? So maybe like some new health trend is affecting things, but there's also some brand problem with another one. Now, hopefully, what the sense that you're getting as I go through this long list is, boy, if you really wanted to do this properly, it would be a pretty complicated problem, right? And that actually is exactly the point, right? Is that as you add more and more of these things that could be explainers as to what's going to happen with ice cream, right? You get into this very, very complicated, like it could be this, but there could be some threshold for temperature and stuff like that, and it becomes a very, very complicated problem. And traditionally, we've been very bad at being able to estimate those things and make a good prediction. And it turns out that deep learning does much, much better at that. And that is really what is behind the AI black box and why it is so successful. Okay, so let's actually think about this a little bit. And I want to sort of point to this little bit stylized graph here. You can just sort of see my pointer there. So this is a stylized graph that people often show when they want to talk about a neural network, or which is really the architecture that most modern AI is based on. And when you show it like this, I mean, it seems kind of futuristic and cool, but actually it's not super, super complicated. All you have is, on the left-hand side, you have these little circles, which are nodes, and those are inputs to the network. So you're saying, like, I'm going to give it some piece of information, so that might be the sales for some particular week, but you could also have, for example, the temperature prediction for the day, the customer sentiment score, etc. Right? You can just, any of these things that you put in. And then, anytime you see a line here, you can think of that as being, you're going to do some little piece of math, right? It's not super crucial what it is, but you're going to do some math, and if you see converging lines here, that means you're going to take sales 1 and sales 2, and you're going to combine them in some kind of calculation that combines the two of them, right? So we said that interdependency matters a lot here, right? So you can imagine if you had sales for week 1 and week 2, you could bring those together to say, well, what's the trend? Are sales going up or sales going down? Okay? And so what you can see here is that the way these networks are set up is like your customer sentiment score can interact with your sales last week or whatever else you put in here. And all of these can feed into some calculation that leads to the sales in the next week. Okay? Now, you might say, like, okay, like, you know, seems like a big complicated thing you could do. It's not obvious at all to me why this is going to work particularly well. And in fact, you know, it was not obvious that it was going to do well. For many, many years, neural networks did not do well. And then at some point, they got big enough and complicated enough that they were able to capture these really complicated things, like the demand prediction for ice cream, right? And all of that interconnection suddenly made it a very, very powerful technique. And so this is why, like, even though deep learning, the technique that is behind the modern AI revolution, has been around for 50 years, it is only in the last little bit that these networks have been complicated enough that they really captured all of the details here. Okay, so just to make that a little bit more explicit, because this is called understanding the black box here. So you can think about, as you take this network and you make it bigger, one of the things you can do is you can add more inputs, and that's going to make the network, what they call it, wider, right? But you can include lots and lots of things. And so when this actual supermarket, they had hundreds and hundreds of characteristics. So they were looking at what was going on Twitter, all of these different kind of things to bring it in. As I said, whenever you have these multiple lines, that's capturing interdependencies. That's really, really important. And then finally, if you have more and more of these networks, where each time you're doing that, you're combining other things, that's allowing you to sort of do more and more complicated modeling for what's going on. Okay, so all of these things are hopefully pointing you in this direction of saying, boy, it looks a lot like as these networks get bigger, they're going to get more powerful and be able to do more things. And that is going to be one of the very central themes that I'm going to talk about today. Okay. So it turns out that this same architecture that I just talked to you about doesn't just work for supermarket demand. It also works for lots of other things. And so you can take a picture, and you can say that each, if we think about like this particular picture here, right, that first little pixel on the top left-hand side, that's just white, right? You could have a really big input here, and that's pixel 1, that's pixel 2, and you're just counting across. And it turns out, if you do that, you can do a good job predicting whether what you're looking at is a cat or a dog. Okay? It's the same architecture. Now, you might say, like, there are sort of current twists on that, if you've heard of transformers or things like that. Those are sort of older versions of that. It is still effectively doing the same thing, right? All we're doing when we're doing this is doing this calculation as we go. Transformers are just a little bit more efficient way of doing the same thing that we're just talking about right now. Okay, so this architecture gets more powerful as it gets bigger, and it's very versatile. That's super, super useful, and that's why AI has taken over so greatly. People may remember, if you go back to 2010, if you looked at a lot of different things that we currently think of as AI, they were actually being done in very, very different ways. So for example, facial recognition was being done by a whole sub-branch. Voice recognition was being done by a different branch. All of these different areas, they've all come together using deep learning because of this, because this architecture is so useful for doing this particular problem. Okay. All right, so the thing that kicked that off, that led us down this road of realizing how important deep learning was this paper. So this data set right here is called ImageNet. This comes out of Stanford University. That's about 1.2 million pictures of stuff from the internet, right? Cats, dogs, cars, whatever. And each year there was a contest to see who could do the best job at interpreting that image. And in 2012, this paper from Jeff Hinton's lab at the University of Toronto came out, and it won. And it was the first paper that had won with deep learning. And that was ever after, all of the winning examples of this contest have all been won by deep learning. So that's, if you felt like this was an incredible rush, it absolutely was, right? It went from this technique was not in on people's radars to suddenly it won by a lot, and every subsequent model that has won has been one of these. Okay. Now, if we think about then the things I've just told you, we can combine them to say, well, let's think about how these models are actually doing over time and what's driving them. And so this is some work that we did in my lab a number of years ago. And so here's what we did is we said, okay, we're going to look at the error on ImageNet. So remember I told you it's just pictures. So I show you a picture of a cat. You say dog, you got an error. You say cat, you got it right. Right? And so this is the percentage error that you get in that. And you can see that paper in 2012, I was getting about a third of the answers wrong. And what we're plotting here is the best performing model on ImageNet in each year. And so each of these dots represents one of those models, and the line represents the trend over all of the models that are being done on this data set. And what you can see is, boy, it looks like a pretty fantastic story, right? It's going down incredibly fast, and you can really see here that it has this nice predictable curve taking us down to saying, oh, well, by something like 2026, we'd be down to 5% error, and then by about 2029, we'd be down to 3% error. That seems great, right? This seems like something that you could say, okay, we're gonna bet on this as how well it's gonna do. But this actually isn't the deeper underlying trend. This is the sort of surface trend, and there's something much deeper going on underneath it. And that relates to what I told you at the beginning, that these networks, as they get bigger, right, you can actually do a lot more with them. So what I've now done is I've taken the same graph we were looking at just before, so the y-axis is the same, but I've just changed the x-axis here to the amount of computation being used. If you're not familiar with gigaflops, don't worry about it. The only thing to notice here is that if you jump from here to here, that's 100 times more computing, that's another 100 times more computing, and so on as we go. Okay, so these are very big scales in terms of the amount of computing we're using. And now you can see this is the true underlying trend, right? As we've gotten better in these models, right, we've been using more and more computation. And in fact, you can see that from this model in 2012 down to 2022, so over this 10-year period, you can see that we've been using, perhaps 10,000 times as much computing to be doing these calculations, right? So that is these networks getting bigger, us training them on more data. It is this enormous scale up in what's going on with these models. And when you look at it this way, it's a little more daunting to think about what 5% error and 3% error means. Because you can see now, to get to 5% error, we would need to increase the amount of computation by more than a factor of 100. Or to get to 3%, it would actually be maybe by another 10,000x. Okay? And when I say amount of compute, that may sound a little bit like nebulous. I mean, what this means is like a data center with 1,000 times more chips, right? These are really, really enormous costs that would go involved in this. And in fact, you can also think about this, if you think about all those chips running, you can think about it as the actual environmental cost of providing the energy for all of these chips. And then you get to some pretty scary things. So I apologize, these are North American references. But already in 2021, the amount of carbon dioxide being produced to train one of these models was the the same as the carbon dioxide that the average American produced in the full year. You can see we're pretty close here to the average American carbon dioxide in their lifetime. And if you go further down this road, you get down to, for example, the amount of carbon dioxide for New York City in a full month. Okay, these are just enormous numbers, right? We should really worry about the environmental damage that this is going to do. Now, important caveat to this slide. This is a static view. This says, if we fast forward from when we wrote this paper, and you say, like, if we have the same chips, if we have the same things, here's how you have to scale up. My lab has also done a lot of work thinking about the improvements in these things, so these are changing. But it is still the case that we're talking about an enormous escalation in the environmental damage and in the electricity demands that we have. Okay. All right. So let me actually just make this a little bit more concrete, right? Because I've said that these things are growing. What do I actually mean by that? Okay, so that first paper, remember I told you this is the one that revolutionized everything in 2012, the AlexNet paper from Jeff Hinton's lab. So when they ran it, they trained it on 2 GPUs. Those are the specialized processors that people use for AI, for 6 days. And at the time, this was like, oh my goodness, this is just an enormous amount of compute. Kind of laughable in today's world. In 2016, when Google produced their neural translation stuff, right? Google Translate, very useful. Now, we're using almost 50 times as much, so it still ran for 6 days, but now we had almost 100 GPUs being run. GPT-4, 100 days, 25,000 GPUs. Okay, so GPUs cost tens of thousands of dollars each, right? So these are just enormous costs that we're doing. And this is all because, precisely, we have ever bigger networks, ever more data going into them to do the same things we just talked about, to make these networks more powerful so that they can model more complicated things and pick up either in a picture or other things much more complicated detail. There I mentioned data. We haven't really talked about data, just to give you some sense of how much data GPT-4 was trained on. The estimate is something like 10 trillion words of data, which is about 2,000 Wikipedias. Okay, so the scale of all of this is just enormous. All right, so in terms of the high costs then, we can think of this in terms of monetary costs, right? So even back when AlphaGo won, this was quite a while ago now, the training cost of that was $35 million. Training cost of GPT-4 was $100 million. So these really are very large investments, but we are really only getting started here. So if you actually look at, there we go. If you actually look at what's going on here, people realize the same trend I've just pointed out to you. This is what is often called the blessings of scale. So let me give you one more example of this, and then I'll show you how much this is scaling up. So this is perhaps one of my favorite examples in the power of making these networks bigger. So this is a Google paper from a couple of years ago, and it's a mixed model. So you can give it some text, and it's going to produce an image for you. And the text they gave it was a portrait photo of a kangaroo wearing an orange hoodie and blue sunglasses, standing on the grass in front of the Sydney Opera House, holding a sign on the chest that says, "Welcome, friends." Okay? That may sound kind of quirky. It's intentionally quirky. That's because they don't want it to be a picture that actually exists in the world. They want to force the system to create a brand new picture, right, and not just be able to recapitulate something that is already seen on the internet. Okay? So what happens if you train it with a smaller network? Okay, so this is a network of 350 million. Remember I showed you all of those parameters, all of those links in that network? You know, that small, in this case, is 350 million of those. All right? But 350 million of them, you get this picture of something that looks not that much like a kangaroo, maybe more Chihuahua, right? Is that the Sydney Opera House? No, probably not. That sign definitely doesn't say the right thing. Like, this is not that good. Same training, make the network 750 million. The network is just bigger. It can capture more of those interdependencies we talked about. Okay, so that's now a kangaroo. It's not the one in the orange sweatshirt. that looks a little bit more like the Sydney Opera House. So we're getting closer, but we're not that close yet. Same training, a bigger network, 3 billion. Okay, now we're starting to get somewhere, right? That looks like a kangaroo. That's like the Sydney Opera House, still not quite right. The signs are not right. 20 billion? Pretty darn good. Okay? The sign is right, the kangaroo is right, Sydney Opera House is quite good. All of a sudden, we can do much, much better. Okay, so this tells us why people have been willing to spend $100 million on this. And in fact, more to the point, why people are willing to spend a lot more. So Anthropic, one of the big companies in this area, has just said that leading AI models will soon cost up to $10 billion. And what he says is this is like in the next year or two. To put this in perspective, the Palm Jumeirah that I visited just the other day, that was 12 billion. Okay, so the scale of investment people are talking about today to train single model is the cost of the whole Palm. Okay. Sam Altman, CEO of OpenAI, recently sought trillions of dollars in order to be building new chip factories, for example, because he anticipates using so many chips to train these other models. Okay, so the scale of these things is just enormous. And that's why it is that scale up that has been so powerful. But that scale up is also the risk, right? Because we've just talked about the economic costs of this, the environmental costs of this. All of these things are going to be playing, and they're going to be a challenge as well. All right. So I just want to then come back to this example we started with and say, well, what went on here? Well, what happened was the prediction error dropped by a third. That should now make sense to you, right? That interdependency that we just talked about, that you can take a whole bunch more inputs, right, and you can connect them in these really intricate ways, that's super useful because it does turn out that ice cream demand depends on temperature and social media and sports and all of these other things. You can bring those things all together, that makes a big difference. Also, in order to do that, in order to have all of that training data and that big a network, right, it can cost you a lot. And when we really dug into the economics of this, what turned out, the reason that they had paused it was that there's some things where all of that additional cost is not worth carrying around. So if you're trying to predict the demand for a can of tuna fish, that can of tuna fish can sit on the shelf for an extra week and it doesn't matter very much. So it is not worth spending a lot of money trying to get that prediction exactly right. If you're talking about some meat or some fish that you bought fresh, there it matters a ton, right? And so what we're starting to get in here is this division between saying the costs are now high enough for this computation that we should pay attention to them and only use AI in some cases and not other cases. And we haven't traditionally thought about it that way because we traditionally think about like, oh, we ran Excel. The amount of time and energy it takes to run Excel is not something we pay attention to. But we do need to pay attention to it with AI because these systems can be so big and so good. All right, so I just want to finish by just a final then saying, well, if we take this model that I've just given you and think about what this is going to mean in the future, well, it's going to mean the following. So if we think of the cost of building a system, and then we think of the year that it's going to be, so what we're going to have is the cost of these cutting-edge systems continuing to grow, right? That's the $10 billion price tag that we just heard from Anthropic. And that's precisely because we need to keep scaling up in order to get better performance. And that means that if you are a business or a government and you're trying to have cutting-edge capabilities, you really need to be thinking often about a very, very big price tag. But there's a flip side of this as well, because there's also the cost of a given level of performance. So you'd say, well, maybe someone has done something and you cost it out like the supermarket, and you say, actually, today we can't afford this. But actually, you can nevertheless project it forward and say, at some point in the future, it will get cheaper. And that's because the cost is going down because there's more efficient AI hardware. So people may know NVIDIA has been producing ever greater chips that brings down the cost of training these models. And my lab has done a bunch of work looking at efficient algorithms, and you also see lots of algorithms being in that are better. And so that's driving down costs. And so what this means is that, if you are an organization planning for AI, you need to think about saying, well, where in this chart do we want to be, right? Do we want to be at the forefront? If we want to be going up on this red line, then we need to be thinking about what's the data, what's the GPU situation we have that can bring enough together so that we're going to be able to outperform those other models. And we now have this very clear roadmap for how to do that. Or you want to say, okay, actually we're going to be on this blue line, and we can think, oh, today we can't do this, but in 2 years we will be able to do it because it will now be a story. And so I think this is the roadmap that it starts to allow us to say, AI does not have to be completely unpredictable. It can be predictable, and if we understand it, we can actually harness it in a way that's going to be right for each of our organizations. Thank you.